Now, what is work? Well, our standard vocabulary, the vocabulary that we use every day, um, tells us that work is anytime we exert ourselves. If I push on something, we tend to think of that as being work. It turns out that's not the physics definition. I would argue that if you were to exert yourself on something, if you were to push a wall or push a block or something like that, that you're not necessarily doing work, you're just creating a force. So the exertion on something is more of a creating an applied force, not necessarily doing work. Work turns out to be, and I'm going to give you the real definition, and then we're going to go back and we're going to simplify it. That's work. The integration of force.dr. Dot product. There's a section in the math about talking about dot products. It turns out that all we're going to do is we're going to concentrate on force and the displacement. Remember, r is representing a positional vector, a general positional vector. So we're going to be concentrating on forces in the direction of r. So both of these are vectors. But the outcome of it is a scalar. It's a number. It doesn't have a direction, which makes this a wonderful tool. So we're taking something complex like a vector. We're taking all that information from a vector, and we're going to condense it down into a scalar, saying, now that I have all these directions in mind, and I've been keeping track of that, I want something simple. So the scalar is going to be this number, and it's going to make our lives easier. Okay, so f.dr. So what does that mean? Well, that means that I'm going to take my force vector, and let's imagine I'm applying a force in this direction. And I'm going to keep track of any displacement that happens in that direction. So if I'm applying a force on a box, and that box, I'm going to use a different color marker, and that box experiences a displacement, remember displacement is a change in its position, in that direction, then we can say that the work being done is equal to that force times that change in distance, or that change in position, its displacement. That's what work is. Now we got to be careful though, because we are talking about forces and displacement that is in the direction of that force. Now that also means that direction, being the x direction in this case, that also means that we can experience a displacement in this direction. Okay, I can apply a force this way while an object continues to experience a displacement this way. Automobile is a perfect example of that. I'm driving in a car and I slam on the brakes. I'm applying a force that is attempting to slow down my vehicle. So if I'm moving in this direction, I'm applying a force that's in this direction, but my car continues to move. So there is work being done there. And it's in that direction. I'm applying a force this way, but my car, or I apply a force this way, but my car continues to move this way. It's still in the same direction. It just happens to be a negative direction. Okay? So when we look at that change in position in this case, then we can say that that's force times that change in position, and that may be a negative value. That may be a negative value. All that means is that I end up with what we call negative work. Okay? So that force is in this direction, its displacement is in this direction, so that means that it's negative work. I'm doing negative work. Now what would that mean though? If I apply a force in this direction and the object is still traveling in this direction, would I be attempting to speed the car up? Would I be attempting to slow the car down? I mean, if I applied a force this way and the object or the car continues to move this way, I'm slowing the car down. So that's where this idea of negative work is coming from. Am I moving the object any faster in this direction? No. No, I am not. I'm not attempting to speed the car up. I'm attempting to slow the car down. So the force that I'm applying, the work that I am doing by the brakes, that's what I mean by the work that I'm doing, is attempting to slow the vehicle down. Okay, now when I'm saying slowing it down, I'm referring to not velocity, I'm referring to speed. Okay? So, vector, vector, scalar. Okay? So, that's what we talk about with work. Now, when we stop for 1 second. So, it's possible for both to do positive and negative work. Now, one thing that we should be careful about. So, here's my diagram again, and I'm going to change this. Now, it's another block. Okay? So let's say this block is on a table, okay, and I'm pushing that block across that table. Now we go back to our free body diagrams, what forces are acting on it. Well, let's say the surface of the table is rough, so there's a friction force. Here's my applied, here's my force of friction. Okay, and then we have a gravitational force that's pulling it in this direction, and then we have a normal force that's in this direction. So I'm going to rewrite these so that it's an actual free body diagram and not just some randomness. So here's the force that I'm applying. Here's the force of friction. Now here's my normal, or here's my gravitational, here's my normal. And we know that the normal and the gravitation in this case are going to equal each other out. The block isn't accelerating through the table or off the table. So, okay, so those are all my forces. Now, looking at that definitional work, force times the distance that, or displacement that it travels. See, I'm going to constantly catch myself on that one. It's not distance, it's displacement. So when we talk about the work that's being done, we have to talk about all the forces that are interacting with that object. Okay, so the applied force, we've already talked, is F times the force applied times the distance that it traveled. Now I said that there was a distance, and got to change my color of my marker. So it experienced a change in distance, or change in displacement, or not change in displacement, change in position of that much. So I can say that the work done by the force applied, the work done by me in this case, is equal to the amount of force that I applied and this change in position. Okay? Cool? Now the work done by the force of friction. Well, the force of friction, Ff, here's the work done by, change this, work by me. Now the work done by the force of friction equals the force of friction, not the force applied, the force of friction times that change in displacement, or the change in position. Now they're both pointing in opposite direction, and I know that this is going to turn out to be a negative value. I know that because they're in the same direction, that this is going to turn out to be a positive value. So I have a negative amount of work done here and a positive amount of work that's being done here. Okay, so I'm doing positive work, the force of friction is doing negative work, just simply by this displacement. This arrow is telling me that the object is moving in this direction. So all forces that are moving in this direction are doing positive work. That means also that all forces that are in this direction are doing negative work. Okay, so I got a positive and a negative. Now I also have two new forces in here. I have a normal force and I have the gravitational force. So if I were to talk about the work done by these, well, it's force times the change in that change in that position. So there's the force, and here's the change in position. But this is where the dot product comes into place. This F dot dr is referring to all the forces that are in the direction of that displacement. So when I do the multiplication, I have to keep track of only the forces that are in the direction of that displacement. So this gravitational force in this case, because the displacement is in this direction, that means that this gravitational force is not doing any work. Because the displacement is in this direction and gravity is in this direction, we think of all the forces that are in the direction of R, and those are the forces that we're keeping track of. Everything else is not important because this is not in the direction of this, it's not important. So it turns out the work that's being done by gravity is zero. It doesn't do any work. Okay, so that's how it gets simplified. I'm already ignoring two vectors because this normal force is not in the direction of that. So it's going to do no work. So the work done by gravity and the work done by normal, we just don't worry about it. It just goes away. Boom, boom. They're not forces to concern ourselves with. Okay? And then when we want to talk about changes in motion, or the net work being done by an object, we just say the work done by me plus any of the other work that's being done in that direction is the total work. So all of this work and all of this work, add that together and you get the total work. Be careful. This is a negative value. So this positive plus this negative, I'm actually going to be subtracting that work out from friction because it turns out this right here is negative and this is positive. Okay? So that's how work is actually going to make our lives a lot easier.